Welcome back. In this lecture, we shall discuss linear regression. And so by the end of this lecture, you should be able to describe how a linear regression model makes inferences. Now, linear regression should be familiar to just about all of you because, nowadays, many people do a basic linear regression task in high school, usually as part of something like chemistry or physics. And you may remember getting a bunch of points, maybe plotting them in a software like Microsoft Excel, and coming up with a formula y equals mx plus b, or in the case what we're showing here, function f of x equals wx plus b, where w is the slope and b is the intercept. Now in machine learning terms, we will call w and b parameters. And that is what we'll be learning from historical data. So when you did that simple Excel regression back in high school, it produced that line for you. It was actually learning that line from the data points you had. And this is a model because the whole point of having that line is if you had some new piece of data, you wanted to predict that y value. And you're doing it based on the slope and the intercept. What's really cool about a parameter-based model like this is you could imagine whether I have 10 samples or whether I have 1,000 samples or even 1,000,000, if I'm learning this simple relationship, I'm always going to have the same number of parameters, regardless of how many samples I have. So throughout this course, we will use w's for all our parameters. So b will be w0, not associated with the value, and w simply stands for weight. Now, looking back at our earlier discussions on historical data, this is a supervised approach. So we will divide historical data into training data, where we already know the answer, and data we will use to train the model. And so, in the case of our diabetes data set, each sample in the training data corresponds with a diabetes patient. Likewise, the features, these are the measurements or attributes associated with each sample. So in our diabetes data set, these are the demographic bits of information associated with each patient that we're going to use to make our predictions. And finally, a target value, and this is what we're trying to predict. So in this case, the quantified measure of disease progression. So now we'll go through a bit of notation, and this is very important because this kind of notation we will use not only in this module on regression, but throughout the entire course. So if we have one feature, as you've already seen, we will have a function that looks like this, where we have f of x1 equals w0 plus w1 times x1, where the w's, of course, are parameters. And now if we have multiple features, we will annotate the w's as wi, and we will just look as a sum over all wi's multiplied by xi's, and we will assume that there are m number of features. Now we can also write this in a vector notation, where we have the transpose of a w vector multiplied by an x vector. And both of these vectors are column vectors of size m plus 1. And note in the x vector, we will always set x0 to be 1, because it's not based on a feature. That's used to allow us to learn a bias from the data, that w0. Now m is the number of features, but this word is also, or this number is also referred to as the dimension. And you might hear things like the dimensionality of a machine learning problem. It's interesting to think about the dimensions of a machine learning problem because we show in examples where we do things with 1, 2, or 3 features because we can easily visualize it on a graph. but really the feature space is a hyperdimensional object. So if you have, say, 20 dimensions, you have this 20-dimensional object, and points within that 20 dimensions, wherever they're plotted, is where a given sample would lie. Now, of course, as humans, we can't even visualize 20 dimensions, but this doesn't make any difference for a computer because it doesn't have to visualize it to draw conclusions. So we shall assume that there are n number of samples in the training data, and we will have an x vector associated with each of the training samples. And within that x vector, each position in that vector is associated with a value for that feature. So a given xi, capital Xi, is a sample. Now for that, we might have a lowercase x, as we've seen earlier, and that is associated with a feature value within that sample. So this is hopefully enough to get you started on your voyage here in understanding the regression model. Stay tuned for more content.